Cool. Hey guys, it's Jesse Kovarovics from Project FDL. You guys may know me as the designer and creator of the FDL1, FDL2, and most recently the FDL3. So we have been printing and designing fully 3D printed blasters for, I don't know, about 5 years now. And 3D printing is really kind of my main hobby, but I use NERF as a conduit to do all of the 3D printing things that I really enjoy doing, and I really enjoy NERF too. So, but what I wanted to do today was kind of do like a 101 video, and get any of you guys who are like considering getting into 3D printing kind of up to speed on how it works, what you're dealing with, what you're getting yourself into. If you are here for like really fine-tuned settings, tweaks and things like that, it's maybe kind of boring to you. It's really like I want to show you what a printer is, all the parts on a printer, what makes this printer different than other printers, what we do, and kind of focus on what we're going to do in the hobby and the machines that you use, particularly in the hobby. This is a talk that I've given like to kids at schools and stuff a number of times, but I know most of you guys are a little older, so I'm going to try to be a little more eloquent about the way that I explain things. And my talk is usually about 20 minutes long, so I'm going to try to drive this out into an hour and a half best I can. So I have my little cheat sheet over here. Sorry if I look off the camera. Let's get into this. What is 3D printing? So 3D printing in general is called an additive manufacturing process. That is, we are starting from nothing on the 3D printer, and we are adding material over time in order to build up a physical model of something that's been modeled in digital space. So this is different from like a CNC machine where you have a cutter head that cuts away from a block of material, be it metal or plastic or whatever. So we are doing the opposite thing. Like I said, you're adding things layer by layer in order to create something physical. So the method that we use most often is called FDM. So that stands for Fusion Deposition Modeling. You also hear FFF, which is Filament Fusion Fabrication, something like that. I don't remember the words often. So that means on a printer like this, you have filament that comes on a spool like this, and it looks a little bit like, you got a roll of weed whacker filament or whatever. This particular spool is called, the plastic is called PLA, so that's polylactic acid. This is actually created from corn and sugars like that, and it also has the same thing in it that you milk stout lovers enjoy. Keep that in mind. There are different materials that we use. In general, though, what you are using is called a thermoplastic. So a thermoplastic, you can heat it up, and it turns into a liquid. And then as it cools, it turns back into a solid. And you can do that repeatedly a number of times before the structure of the material actually starts breaking down. It works really well, and it's really perfect for our situation here. There are lots of different materials. We use a lot of PLA because it's very easy to work with. And I would suggest if you're getting into this, you probably start with PLA. But you can also use PETG. There is ABS. ABS is the material that most store-bought NERF blasters are made out of. And there are a lot of other plastics used on top of that. But those are sort of outside of the scope of what you can generally do on a consumer 3D printer. So the different types of 3D printing, like I said, we're focusing on FDM printing. That is what this machine does. There is also SLA, which is where you use like a resin, and then you have a like UV light that actually cures the resin and turns it into a solid. There is no moving back from that. There is no taking a solidified resin and turning it back into a liquid resin. That's kind of the difference between using the thermoplastic and SLA. SLA can be much more precise. It can be much more fine and give you kind of a smoother surface. You have some sort of strength differences there. And the process and the machines that you use to do that are very different. They're probably a little bit more expensive. That is an up and coming technology that has been in the process for a long time, but we're starting to see those machines being really consumer friendly as of late. And then you have SLS, which is selective laser sintering. So that is, the most common form of that is if you had like a vat of metal filings. So think about like, iron filings in a little vat, and then you had a laser that actually zapped those and sintered that powder and turned it into a hardened metal. And then there are other ways that this works in general too. Again, we're going to focus on FDM. So in terms of printers, this is my good friend Carrot Top. This is a Prusa i3 Mark II. So it's not a Mark IIs, it is not a Mark III, it is not a Mark IIIs. This is actually a relatively old printer. This guy has been printing 24 hours a day for almost 5 years now, and he has just reached the point where I have to take him out of commission, which is really unfortunate, but he's done a really good job for long. So there are lots of different shapes and designs of printers. This in particular, and most of the printers that you're going to see, probably 60 to 70% of the printers that when you go out to buy a printer are going to be what's called a Cartesian printer. Cartesian, if you remember from sixth, seventh grade, you learned about the Cartesian coordinate system. So you have an X, you have a Y, and you have a Z that goes up and down. So everything operates in straight, perpendicular, or parallel fashion. The other versions of printers, and we only have Cartesian printers here, so I don't have something to show you, but there is also what's called a delta printer. So rather than this setup, you actually have 3 posts, and then the machine moves up and down those 3 posts, and the action of that motion moves your extruder head around as well. That tends to be really nice for like curves and things like that. And the way that those are designed, they can actually be as tall and short as possible. They're a really good choice of printer if you are going to print very, very tall things, or if you're going to print a lot of circles or things like that. Deltas are pretty common. You can get those pretty easily. The other type are polar printers, and this is like really rare. But if you look at this printer, right, you have left, right, up and down, and back and forth. So a polar printer, instead of this going back and forth, you would actually have a platform on the bottom that spins around. This can be a little more simple, right, because you're only dealing with how far your print head is away from the center of that circle and where that circle is in rotation. Those are rare. I don't think I've ever even really seen one of those outside of like the Google search that I just did before this video. Your other type, and this is the more abstract type, is your kind of robotic arm. So this is anything that doesn't fall into those categories. It could be the typical robotic arm that you're kind of used to seeing, like in an industrial situation or something like that, or a SCARA arm, where you'd have a central post, and then the arm kind of rotates on that. There are advantages and disadvantages to that. A lot of those, the motion control and the math of that gets really out of hand. But if you ever go to like a 3D printing convention and you meet somebody who is designing those things, that's the dude to talk to. That's the market. So back to this printer. This is a Cartesian printer. This is designed by Joseph Prusa, but this is, because it's called an i3, so the i3 stands for the overall design and the makeup of this machine. The i3 actually is his 3rd iteration from some of the original printers. So the original printers were like, there's some threaded rods and stuff on this thing, but it was like all threaded rods and just printed pieces. And that all came from the RepRap project. The RepRap project was, how do we create a machine that can create pieces to create another machine? And it's this kind of like cyclical design creation sort of process. So Joseph Prusso was one of sort of the original pioneers of a lot of the 3D printing, in particular, moving 3D printing into a setting where you can do it at your home, on your desk for not a ton of money. That's a relative term, but like in a amount of money that is accessible to most, common people. So yeah, this is an i3 design. So you have, this tower that's straight up and down. You have a gantry here where you can move left and right. This moves up and down, and then your y-axis, the bed that moves in and out. I'm going to move here. Okay, the printer that I started on is this. This is a PrinterBot printer. So this was one of the PrinterBot Simple Metals. I'm so sad to say that this company is not in business anymore because I really enjoyed these printers. This was the first printer I bought, and this printer came about at about the time that 3D printing started becoming relatively easy. Prior to these printers, things were very like hit or miss. Things might work well, they might not. Things were very kind of ghetto a little bit. But the nice thing that PrinterBot did was they created a printer that was fairly easy for people to use. And you'll notice if you look at the design of this printer, rather than the bed moving forward and back, it moves left to right. So we've moved the x-axis down onto the bed instead of it being on a gantry on top. And then your y-axis is this cantilever arm that kind of sits out and cantilevers from the base here. Z up and down is the same. So that's sort of an example of like a different printer. I miss these guys. These were really nice. All right, bring Carrot Top back up. So what I wanted to get into next was basically the anatomy of a printer. Again, a lot of you guys who have been printing for a while, you're like, yeah, we know all these pieces or whatever. If you are sort of in the market and you're considering getting into 3D printing, I think it's really important to understand kind of what's going on here. I picture a 3D printer as a tool, right? It's not a toy. It's not just a thing that you have. Like, it is a tool that completes a job that you need to do. And all of the tools that I own, I get really into what's in the tool, how they work, and everything. And it's important from like a troubleshooting standpoint when you're trying to print. How the heck do I get this thing to work? To understand what's going on inside of it. Also, if your printer breaks down, it's really good to know how to repair it as well. Because truth be told, there's not a single printer on the face of the planet that is perfect. They all break down at some point. They all have problems, and as nice as these Prusso machines are, they have problems too. The way that we have been able to print so well for so long is I've learned the ins and outs of this printer, and I can maintain them really, really well and keep them running constantly. All right, so where do we start? So the printer as a whole is, I guess in the development world, you would call this an embedded system. An embedded system starts, turn him around, be back here, and unfortunately he's black, so it's a little hard to see. But there is a box here, and the box holds the main board for your printer. On the PrinterBot, those look a little bit like this. So this is it's just a board with a microcontroller on it. That is essentially a glorified Arduino. So an Arduino, or like a microcontroller, its only job is to run the program that is put on it. And it just runs that, and it loops over and over and over, and it takes simple instructions, and it just does its thing. That is very different from something like a Raspberry Pi. There's no file system on this. There's no operating system. There is nothing. There is strictly just code that is on there that needs to operate the printer. So this particular board, and if you look at a Arduino like Mega, it looks very similar to this. And actually this chip in the middle, I realize you can't really see anything I'm doing, but the chip in the middle is the same chip. And then you just have a bunch of spots where things plug into. If I was to open up this box, you can see that same board sitting there, you know, with a bunch of things plugged into. So that's the brain of your 3D printer. How the 3D printer moves, there's a black cube right here, and underneath here where you can't see it. These are stepper motors. Stepper motor, so like the difference between the motors that you guys put flywheels on, or things like that, those are DC motors. So you just apply a current to it and the thing runs at whatever speed it's expected to run at. Stepper motors are a little different. Like I could apply a current to that thing, but it wouldn't move at all. There's actually an additional driver that is on that board that I just showed you, that every time you pulse that driver, it turns that stepper motor just a little increment. And I believe there are 180 or 220, I'm forgetting right now, the increments in a single rotation of it. So that is how a printer can be so accurate and consistent and precise all the time, is it's controlled by these little tiny pulses that make that motor move just a little bit. So there are motors on each axis, and you can actually see if I move that quick enough, you can actually see the LCD light up, because every motor in reverse is actually a generator. So there is a motor on this axis. It's over here. There is a motor right here that is on your extruder axis. So your main board there is talking to those stepper motors, and they're moving all the time. Now, in memory on that board is the position that this machine is at all the time. So if I move this all the way to the left, you actually hear a little click because there are homing switches at the end of here. The machine has no idea where it is at any given time until you move this all the way to the left and it hits that switch. Now it knows that that axis is at 0, right? So as precise as like a stepper motor is, it still relies on a switch on the machine to tell it where 0 is. And there is one of these switches on all 3 axes. The switch that is on the Z-axis is not like a clicky switch, though. It sits right here. Sits right there, and that Prusa calls this a pinda probe. I don't know what the actual name for those is, but it's actually a sensor that can sense metal. So if you were to tear apart this bed here, you'd see that there are little metal spots on the bed that when this thing drops down, it can sense, oh, there's metal directly underneath me. You can actually screw the printer up by putting like a little coin or something there as it's doing its thing. But that acts as the switch for the so that is the motion of the printer. Other little things, there's a power supply back here. So the power supply is a lot like the power supply that you put in a computer power supply. Same thing, very simple. On the front, there is an LCD screen that gives you, as the user, a visual feedback and way to control what is going on inside of the system. The printer bot that I showed you before doesn't actually have an LCD screen on it. So we actually have Raspberry Pis hooked up to the printer, and those control the printer and tell it what to do. In this situation, you have an SD card that goes in the side of here that contains all of your G code that tells the printer what to do. We'll get into what that is. So the next big thing, this whole section right here, this goes by many names. A lot of people will call this an extruder. A lot of people will call it the hot end. What this really is your print head. Okay. But inside of the print head, you do have a hot end, and the hot end is down here. I actually have that. This is the hot end from the printer bot. What's inside of a Prusa is a little different, but it works basically the same. So, you have your roll of filament that sits up here, right? And the filament feeds down in. And on the top, above this point is actually your extruder, right? So the thing that this motor does right here is there's little knurled knobs inside of here that grip onto the filament, and as that turns, it pushes the filament down inside of the hot. The end of your extruder is your nozzle, and directly above that there is a heater block. And the heater block's purpose is to melt that plastic. If you look at most hot ends, this black section right here has a bunch of fins on it because it acts as a heat sink. So the thing that needs to happen is the filament gets fed into your hot end, and it needs to stay cool all the way down to where it is heated down here. If that heat creeps up inside of your hot end, you start getting issues, and molten plastic can kind of leak up out of it and stuff. So usually you have a fan, the fan right here on the side of it, that actually blows across the heat sink, and it takes away that excess heat, such that that excess heat stays only down in this hot transition zone. So on the end of the hot end, you have your nozzle. So your nozzle is essentially, I like to think of this as like if you're icing a cake, right? Your nozzle is the end, and there's a tiny hole in it. And as the extruder pushes the solid filament down into the top, it gets melted and then pushed out through the nozzle on the end. Most consumer machines that you come across will come by default with a nozzle that has a 0.4 millimeter diameter hole in it. That is pretty much a 3D printing standard size. You can get nozzles that have bigger holes or smaller holes, depending on what you're doing. A bigger hole means you can push more plastic out at a time, so you can actually start to print faster. Your layers can be a little higher. Or you can get smaller ones if you're doing very fine detail. So yeah, so like I said, this is the print head. The print head is actually made up of an extruder and a hot end. That is about that in terms of anatomy of the printer. So I kind of mentioned before that the machine is really dumb. It really doesn't know how to make the thing that you're telling it to make. At no point in time do you put here's my model of my super cool, blaster. I'm just gonna stuff it inside the printer. It would have literally no idea what to do with that. It would just be like, cool, you gave me a bunch of bytes. I don't know what to do with it. So how the printer actually operates is off of a thing called G-code. G-code, if you opened up a G-code file, I kind of wish I could show you guys this, but if you open up a G-code file, it is like millions of lines of very, very simple commands that the printer does know how to do. So what this thing does know how to do is, cool, I'm at X, 20X or whatever right now. If it is issued a G-code command of go to 40X, it knows I'm going to move over 20 millimeters or whatever that difference is there. That G-code can actually tell the printer to do a lot of things too. So, typical up and down axes, it controls the speed of your fans, it controls the temperature of your hot end, which is something I didn't mention before too. Your hot end has what's called a thermistor in it. So a thermistor is something that measures temperature. It's actually a resistor that changes its resistance based on how hot it is. And it can use that to tell the main board how hot your hot end is. And then there's an algorithm that happens in the board of okay, we got up to 200 degrees Celsius, shut off that hot end, and it dips down, and then when it gets to a certain point, it's turn it back on. This PID algorithm goes up and down, not important. What we are talking about is G-code, right? So this thing is really dumb. It only knows how to act on G-code. So on this printer in general, I mentioned that there is an SD card that goes in the front. That SD card has G-code files. Like I said, if you open up those G-code files, it's a series of instructions, lots of these things in a row. So the way that this machine in general works is it has that SD card, it reads the G-code files, and as it's printing, it's just slowly churning through each of those instructions. And when it gets to the end, it's done. On the printer bot, I said that we use a Raspberry Pi to hook up to the printer. So I could actually hook this up to my laptop that's sitting here too. And rather than reading off of the SD card, I can have the laptop issue all of those commands to the printer. The big problem with that is if something happens to my laptop in the middle of that print, a big one that is an issue is I have a Windows laptop. If Windows suddenly decides to update Windows during the middle of my print, it's going to screw up my print. Using a Raspberry Pi is essentially the same as using a laptop to plug in and issue those commands. The nice thing about a Raspberry Pi is that it's small and it doesn't have Windows. Those are Linux systems, and its sole purpose, being a little tiny computer, is strictly to issue the printer bot those G-code commands. So there's a couple of different ways that you can actually control it. The SD card is actually really nice. In our situation where we're printing basically the same blaster or two, like not a ton of different designs over and over, I just have the same files on each of our cards, and then the other 8 printers that we have in the print room all have the same files in the cards. So you can swap the files back and forth, and it works really well. And also that SD card is dedicated to this machine. There is literally nothing that can interrupt outside of an internal error, the communication between the main board and that SD card. So that works really well. The nice thing about the way the printer bot setup is with the Raspberry Pi, and that's called Octoprint, by the way. I don't want to get deep into what Octoprint is, but Octoprint
They're
is...
talking about it.
Are they? Okay. So Octoprint is, a software. It's a service that runs on that Raspberry Pi, and its strict job is to issue commands. The nice thing about that is each of our Raspberry Pis is hooked up to an internet, and it's hooked up to our internal network in the house. So each of them has their own individual IP address. I can, on my laptop or a tablet or even my phone, I can bring up a web server that's hosted inside of that Raspberry Pi and watch what's going on with the printer. I can tell it to stop. I can issue it commands, through a little command prompt. And there is, because that is a computer that has a network accessibility, you can actually design software and stuff on top of that to do whatever you want to do with it. So that's really nice. But that means, each of those printers is hooked up to a $40 to $50 thing, and it gets complicated. You can have a camera on those too, which is kind of nice. So then you get like live stream. But in terms of like a print farm, it's pretty nice to have stuff on cards, and it's pretty nice to not have them require a network connection. Okay, so that is basically how the printer works. Why it is so dumb, and the simplicity of what is actually going on here. I know, like, when you first get into 3D printing, you're like, cool, I have this machine that does all these magic things. Like, it is so not magic. It's kind of funny. But the culmination of lots of little magic things all plugged together is so fascinating. And I personally just really like machines. If I could have like something that's 5 times the size of this in my house, it would be like Candyland. It'd be like Willy Wonka's back. But this is really nice, and these are really accessible. So let's say that you want to print part that you design. Okay, how does that work? This gets into where I wish I could share a desktop with you, but I think I can walk you through it. So to design the FDLs and like whatever I want to print, and same thing for you guys, this all originates in what's called CAD. Again, something that a lot of you are very familiar with, and in case you are not, CAD stands for Computer Aided Design. So this is a computer software that you can model you can model things in a digital 3D space. And you get a visual 3D representation of the thing that you are modeling. The method of modeling is sort of unimportant, and it differs from CAD software to CAD software. When I started, I have a history using AutoCAD. AutoCAD is a little archaic now. It's used mostly for architectural things. The way that it operates is very different than something like Fusion 360. So Fusion 360 is something that, for the most part, is free. It's made by the same company, Autodesk, so there are ties between the two. Fusion 360 is what's called parametric modeling. So like you would, for example, put a cube on your screen, and then you would put a circle, and then you would connect those two together. But when you put that cube down, you decide what size that cube is. And at some point in the future, when you have 85,000 cubes and cylinders and things all stuck together and cut apart, you can actually go back in history and say, nope, when I first started this, I want to make that cube 20 centimeters, not 20. So there's like a history that happens. And I believe that there are going to be other people that get into 3D modeling, and we'll show you guys Fusion 360. Fusion 360 does have a fairly decent learning curve. Me going from AutoCAD to Fusion 360, I had some history with parametric modeling, but it was an adjustment. So if you've never touched a CAD software before and you jump right into Fusion 360, you may be like, oh, this is super easy. It makes a whole lot of sense. Your other option, and usually when I'm talking to a younger crowd about this, is Tinkercad. Tinkercad, again, made by the same company, Autodesk. Autodesk makes a software called Tinkercad, and Tinkercad is your basically dummies start to 3D modeling. You literally pull shapes in and you connect the shapes together. You can make the shapes bigger or smaller. You can actually pull STLs in. So this is something I didn't talk about before, is the different files. And we'll get into that in a second. So if you have no idea what CAD is, if you've never gotten into it, if you feel like this is a big stretch for you to get into, Tinkercad is a really good place to start, and it's a really good place to learn the basics of 3D modeling and things like that. All three of those softwares, when you are done modeling, they spit out a file that's called an STL file. So that's stereolithography. I believe that's what that stands for. An STL file is a very generic version of a 3D model. So when you're using Fusion, you have all these different commands and history and dimensions and everything. An STL is literally just here's a bunch of faces. This is where the faces point. There's a bunch of polygons. It's a really simple digital representation of a model. So cool, you've modeled your thing in whatever CAD software you want to use. You have spit out an STL file that's a basic representation of your object that you want to print. Your next step is what is called slicing. So the way that this works, basically every FDM machine operates by creating tiny, tiny layers that change over time as they build up. So if you figure something that's printed this tall, maybe has several hundred layers in it. And then each of those layers is created by an algorithm of your print head moving around and creating the shape of that layer. And that shape of the layer can change slightly over time, and that gradually builds up. FDM, Fusion Deposition Modeling, builds up into a model over time. So you have your STL file. You need to turn it into something that a 3D printer can understand, and that is where your slicer comes into play. And you'll learn that there are a series of steps between I made a thing and I made a thing in order for this to happen. So your slicer is an additional software that you take your STL file, you put it in, and it slices it. So it cuts that solid up into little tiny layers, and it also decides how the print head moves around in order to create those layers. And then within your slicer is where all of your quality magic happens, right? You determine how high of a layer height you want to use. Typically, how a 3D print is created is you create a number of perimeters around the outside, and then you fill the inside of your dead space with some sort of shape, be it like a square grid, or like triangles or hexagons, or very complicated and unique, like a gyroid. Like there's all these different shapes of infill that create the structure inside of your 3D print. What structure you use, how many times the printer goes around the outside of it, how fast it runs. There are hundreds and hundreds of settings inside of your slicer, and like the slicer could be an entire like 102 or even 202 sort of talk. I'd love to get into some of that today, but again, this is something that like I'd like to show you the screen to be able to use. I don't think it's really important from the standpoint of, hey, I want to get into 3D printing. What do I get? Where do I start, and what the heck am I getting myself into here? So you have your slicer. You pulled your STL into your slicer. Your slicer has sliced your model up into lots of little layers, determined where the print head moves around. When you are done with that and you are satisfied with the way that the thing works, your slicer is then responsible for spitting out the G-code files that you then put onto your SD card, put into the printer, or onto your Raspberry Pi that is running off the print. Or, you know, sometimes the slicer itself is also a environment where you can control your printer, and you can actually feed the G-code directly out of the slicer into the printer. Again, that gets you in a situation where the printer is reliant on your computer to work consistently in order for that to maintain. But the long and short of it there is that is the purpose of your slicer. Take your model, turn it into G-code, and that G-code then goes onto your printer. Your printer can then understand that G-code and it's given the instructions on what it can do. So that is slicing. Let's talk about some basic things in regards to actually printing, right? So there are a number of different things that separate some printers from other. And one of the big things, and that is really critical to 3D printing, is this print bed. Okay, so when you print, I'm gonna grab it. When you print, you're gonna end up with a thing like this. In order for that print head to properly put down plastic in the places that you expect it to put, this thing has to stick to that print bed. If you figure this is kind of like hot glue, and I didn't use my hot glue gun analogy before. Usually when I talk to younger kids about 3D printing, the analogy is this is a robotic hot glue gun. So even though this plastic isn't really glue, when it is liquid and it sticks to the bed, it sticks to it like glue. And then each successive layer on top of that sticks to the layer underneath. And it creates a super cool model like that. So one of the super critical things of successfully 3D printing is making sure that this piece sticks down to this bed at all times. So you can get different surfaces, different material that goes on top of your print bed. This printer in general has a very thin film of what's called PEI. So PEI is, I don't know a lot about PEI like the science of it, but I know that it is very, very slightly porous while also being very smooth at the same time. It allows this print to stick down very well. But at the same time, when the print is done and you need to pop it off of there, it pops off pretty easily. I have used, before PEI was a very common thing, I used a thing called BuildTack. BuildTack was sort of like this proprietary porous plastic that you could stick down to your print bed. And it was sort of like Yeah, I'll get into that.
Okay.
It was sort of porous, like, I don't know if you young guys really carry folders and stuff around in school, but like when I
Do you carry trapper keepers?
yeah, it's like the old like binders that had this plastic that was like kind of rough but not really. Build tack is sort of like that, and the point was that the plastic would stick down in those floors very tightly. It worked really well. It was a little finicky though. You could actually print too close to the bed, and like it's too much, it'd be hard to get off of there. Other surfaces you can actually use like a tempered glass surface, and then you spray something like hairspray, or use like a glue stick that actually acts as an additional adhesive in order for your part to stick on the bed. The nice thing about PEI is you don't need to use any additional adhesive as long as you keep it very clean. And then, I have bottle. This is isopropyl alcohol. It is 91% isopropyl alcohol, so it is 91% that, as opposed to that extra 9% water, which is really important because even if I do this and I touch this bed, the oils from my hands are rubbing off onto the bed and can actually disturb how well that part adheres to that portion of the bed. And you can even see that, like if we go to print and there is a big old fingerprint right there, like that'll show up on your print and you'll actually see where it didn't stick well to that section of the bed. So we just use paper towels and some of the isopropyl alcohol, wipe it off, make it nice and clean. It's sort of like cleaning the lens of like a camera. You have to get it super, super clean. And as long as you do that, it sticks really, really well. I hear people talk about like using glue stick on these printers and stuff, and I find that like having to use glue stick when your print bed is probably not clean or there's something going on. There are exceptions to that, and that is PETG, where PETG wants to stick to this surface so much that you actually use the glue stick as a releasing agent so that you can get this off later. But that is a whole different talk where we get into different materials. So there are different surfaces, different things that you can put on your actual build plate in order to help the plastic stick down. Another thing that is special about these build plates, and pretty much every printer that you get nowadays, this bed actually heats up too. So this can get anywhere from room temperature up to 100, 120 degrees Celsius. People say you don't really need the heat bed in order to print PLA. I have never found that to be true. You always want the heat bed. Because what happens is as plastic cools, it tends to want to like shrink in on itself. And as it does that, it'll shrink in and it'll actually curl up off of the bed. So what the heated bed does is it helps prevent like a really quick cooling action from the plastic such that it bends up really quick. The heat bed helps keep the plastic slightly molten, but not like liquid, such that it sticks down and it stays on the bed really well. PLA is really nice in that it does curl a little bit like that. It shrinks a little bit, but it's not too bad. It's really easy to work with in general. It doesn't require a high temperature. It melts really easily. It's pretty nice. PETG requires a little bit of a higher temperature. It's a little hard to get finer details out of it. And I know you PETG guys are like, well, you can get super fine detail out of my stuff. That's cool. If you work at it, that's great. But PLA tends to be a little easier to get like a really nice finish. The step up from there is ABS. Like I said, it's the same material that a lot of your Nerf blasters are injection molded out of. That's a whole different process that we could talk about on a different day. ABS is really nice because so PLA, if you leave this in a hot car, mind you, this is like hot car, not like it is 50 degrees outside right now and the light is shining. Like in a hot car, this will actually reach a temperature where it starts to slightly melt. that can be a bad thing. If you have things that are printed in PLA, don't leave them in your cart. Don't leave them in the direct sun in the middle of Atlanta summer. Things like that. PETG has a slightly higher melting point, and it can withstand a lot of those normal occurring temperatures. ABS is well above that. ABS is sort of like this magic material where it has really awesome impact resistance. So like we print our flywheels on FDL blasters in ABS. And like I can take those puppies and hook them against the wall and they won't break. If I did that with PLA, they might break a little bit. But it's a really nice material. The trouble with ABS is it curls like a bastard. And like even having the heated bed here, if you tried to print ABS on this, that heated bed is still not enough to prevent that plastic from curling up and popping off the bed. So usually what you end up doing is actually putting a whole enclosure around your whole printer in order to heat up the entire area that your print is occurring in. ABS prints with your bed wicked hot. For a difference there, like this bed when we run our PLA prints is at about 56, 60 degrees Celsius. ABS, you have to run it at about 100. PETGs, anywhere between 70 and 80 or something like that. So there's a lot of heat going into getting ABS to print. And it's very finicky about like if a gust of air comes by, it'll suddenly warp everything on the ABS. Wild. But it's a really wonderful material if you can get it to print really well. Again, we use mostly PLA because we have an arm running all the time, and we need something fairly simple to print. And also for the most part, unless you were in like this hard desert or something crazy like that, just being outside with a PLA part is totally safe and totally fine. Let's see. We talked about the bed. We talked about keeping things stuck down to the bed. Basic printing terminology when you are printing, and these things start coming into play when you're designing pieces or if you're trying to figure out what settings to use in your slicer. FDM and 3D printing is this really magical thing that you can almost take plastic and just like print it out in dead space and it'll just harden and do its thing. So you can do things, if you look at this piece right here, and this piece prints just like this. So there's a straight face right here, and then it juts out at 45 degrees this way. This printer will do that just fine. It is a really clean surface under here. That is what's called an overhang. When you are hanging over the edge of the last layer that you printed, called an overhang. If you were designing a piece, or if you were trying to figure out how to print a piece, most printers will successfully print at about 45 degrees this way. Some will do more. You could actually tune a printer in to get about 50 degrees or whatever. Some will do it better than others. A lot of that comes down to how quickly can you take your hot molten plastic and cool it down to a hardened plastic. And a lot of that comes down to this fan right here that blows down on that part as you are printing it. So everything that I design, I usually try to stick to a 45-degree overhang on everything, and it prints pretty nicely. Another term, if we had, let's say, for example's sake, we printed this. This section up here, so this is like sort of an upside down octagon. The section that goes straight across there is what's called bridging. Bridging is when you are going straight from one point to another, straight across. And this is where I was talking about where the magic happens. Like, how do you print a molten thing out in space without it dipping down? And as long as those 2 points that it's connecting aren't too far apart, it'll actually just magically do it. It works really nicely. So that's something that you need to consider when you are slicing things. What are some other good
What?
Terminology.
Terminologies for
Printing stuff.
I describe things as verbs and
Yeah.
I mean,
Jackie has her own whole like nomenclature. I guess in terms of tools, yeah, let's talk about that. Like, say you're going to buy a printer. What do you need to buy with the printer? And that's the next thing I want to talk about after this little thing is, cool, I want to buy a printer. What printer do I buy? Because there are like 800 different versions. But something you need to keep in mind before we talk about that is when you buy a printer, you actually need to buy a bunch of other things. The two biggest things that I talked about before are these. Is a little bit of isopropyl alcohol and a roll of paper towels. Super simple. Is this still running? Because it is locked up solid. Okay.
Someone said in Discord that they're going to take a shot every time he says bad boys.
Bad boys. Bad boys, bad boys, bad boys. You are now drunk. The other thing is, when you have a print that is stuck down onto the bed, how do you get that off? Sometimes you have a print that, like this one, it's fairly tall and structural, so I can just like pop it off of there. But sometimes it's a little hard. So I use this, and there are lots of different versions of tools in order to pop a thing off. I like to make all my own stuff. So I sacrificed one of my really nice wood chisels, and I took a little grinder and I ground off the corners on either side. And then this way, you can actually take that chisel and get under a corner and twist it and pop that piece off of the bed. There are a lot of, commercially available products like that. Sometimes they have like a handle, you can get under there and pop it off. You could use like a paint scraper or, a number of things. The thing that you really want to be careful of is whatever tool you use, you don't want to scratch your bed. Like I talked before, if you have fingerprints on your bed, you got a print on top of that, that fingerprint is going to show up. The same way that if you go and you use a chisel like that hasn't had the corners ground off or whatever, and you like really have at it and you leave a bunch of scratches on your bed, when you go to take this off, you're going to see those scratches on top of it. So you want to be really careful not to mess your bed up. Don't scratch it, don't mar it. Be really careful whatever tool you use. Another really awesome tool. I don't know how well you can see this. So this is a deburring tool. This is, there's like a little swivelly cutter on the end of here. And what these are actually used for is if you cut like a copper pipe, and then you feel inside the pipe, there's a burr in there where the metal actually bends over from you cutting. And this is used to scoop around the inside of the pipe and it cleans that burr off. What this is really awesome for, and this is something I didn't talk about before. So when you print, let's say you print right here, right? And you have problems with your print curling off of your bed. There is something that you can use called a brim, where it will put a single layer down on that bed that extends outside of the perimeter of that part. So what that brim does is it creates a little bit of an extra sticking point at the edge. Oh yeah, here's the part right here. This actually, I modeled the brim into this. There's like a little film on the end of here because we have a problem when we don't print this with a brim, at that point tends to curl up. So I actually modeled that directly into the piece. Your slicer will create a brim. It's like a little rail piece, and usually you can just take your brim and pull it off of there. So the deburring tool, what you can do is use the deburring tool to get off any excess brim on the outside of here. And it's really easy, and it's way safer than using an X-Acto knife to cut off of there. Can't tell you how many times I have cut my fingers with an X-Acto knife, cleaning up the brim, and the deburring tool solves that all. I got this at Micro Center. Would imagine that they have it at like Home Depot and Lowe's, like in the
woodworking tools too.
Plumbing section. Yeah, there's woodworking tools and things like that. They're not super cheap. I think it's like $16 or something, but holy crap, what a tool that is.
Oh my God, it's amazing.
Best. That's about it. Like, it doesn't take a lot of stuff to 3D print. There are tools that you need. And that differs depending on what kind of printer you have and like what your print surface is and things like that. So let's get into the bigger topic, right? This is the one question that 8 million people always ask all the time. I want to get into 3D printing. What printer do I buy? Number one question asked by everybody. And this is in the
Is deburring spelled 2 R's?
Oof. Is it still running?
Yep. Well, I'm not playing it while I'm sitting here. Yep. You're still going.
Oh, but my phone is the one. Okay. Sorry. What do you buy as a printer?
It just shifted. You're like, it's only your head now. The top half of you is gone.
Did you touch it?
I haven't touched. No.
Well, then move it so that it can play.
Your camera's in the right place. It's the stream, the secondary thing that it's going through.
All right. Well,
Okay,
I'm
it's
gonna
fine.
keep going.
Yeah, go. It's just it's not printing up. It's not hitting the printer.
It's not important for this. Okay. Okay. What printer do I buy? I wouldn't move that because if it's just part of the stream, your choice of a printer is going to come down to 4 basic things. Number one of those things is the type of material that you are going to want to print. Like I said earlier, there are different printers, like SLA printers that will print resin. These are FDM printers that print thermoplastic. Most thermoplastic works in temperatures that these printers are very capable of, that you can get within a price range between about $200 and $1,200. There are other things like if you want to print nylon or polycarb or any of these really fancy materials, you have to start considering getting a different level of printer. You can do it with these, but you start taxing certain components of your print head and stuff like that. So let's say, for the sake of argument, all of you are going to buy an FDM printer. Okay, so we've gotten past issue number 1. Your next step is your budget. Are you willing to spend $200? Are you only willing to spend $100? Are you willing to spend $1,000 or somewhere in the vicinity of that? How important is the quality? And that's another thing that we're going to get to. But like, I have a table saw in the other room, and I can go to Home Depot and I can get a $100 contractor table saw. It does the thing. It rips strips of wood. It does all of the stuff that I need to do. What I did do is I went and I bought a $600 table saw, where the everything is much more precise. The table is made from like super heavy cast iron. Like, there's a lot of differences between a cheap and a more expensive table saw, and the same thing is very true of a 3D printer as well. So you have to consider personally, what are you willing to spend on a 3D printer? And the determination of what makes up your final price comes from the next 2 things. The next thing is the ease of use. And this is a big one. This is a really driving factor in a lot of printers. When I first bought my printer bot, it wasn't super easy to use. It was easier to use than a printer that I could have bought from a kit, like So then we have something like this, and I really don't want to turn this into like Prusa ad. And I know, Apple fanboys feel the same way that I feel about Prusa. I don't want to be a Prusa fanboy, but I am, because it's really hard to deny the things that you get out of these. So one thing that Prusa does in particular that makes these machines more expensive is they spend so goddamn much dev time on these things. Every single one of these pieces, there are like software engineers in their offices, there are designers in their offices. They have throwing a ton of resources and making this machine the best machine that it can be. And it comes through in the execution of the machine. Like I said, this thing has been running 5 years, like 24 hours a day, 5 years, and it's only now hit the point where I have to take it out of commission. I could probably just swap one piece out on it and it'll be good to go. There are like 3 or 4 iterations after this one, and the newer runs are even better. So one thing that happens when this thing goes to print, okay, and this is the big difference between like a cheaper printer and something more expensive. When this goes to print, it actually probes multiple spots on the bed, and it determines if your bed is level, if everything is square. I mean, this is just like a CNC machine where it's really important that all of your axes are perfectly perpendicular to each other. There are some, when I put this together by hand, it goes together fairly perpendicular, but there is just a little tiny bit of skewing that comes from a machine that's put together with threaded rods, and there's little tolerance things. So what this machine will actually do is probe that bed out and determine how flat your bed is, how perpendicular it is to the different axes, and it will internally mathematically figure out what it needs to do as it prints in order to adjust for your bed being a little out of level. If you picture, if that didn't happen and your bed was tilted this way a little bit, things would stick really well to that side of the bed, and it wouldn't stick that well, if at all, to this side of it. And that's a big deal. That is a big deal in getting your first layer properly down and really nicely executed such that all of your layers after that are executed as well. It's sort of like this chain reaction where your first layer that goes down is the single most important layer of your entire print. And whatever your machine can do to help you ensure that that first layer is absolutely perfect will determine the success of all of the layers following. So this machine, when I first bought it, it was about $800, right? And that's bought from a kit. If you want to buy them completely assembled, it's usually a couple $100 more. I believe that the Mark IIIs and the 3Ss take those two figures and bump them up about $100, $200, to the point where if you bought an assembled Prusa Mark III, it's about $12. Don't quote me on that. If you really want to know, go to the Prusa website and check it out. The other thing that these printers do, and the reason why these are slightly more expensive, is all of your stuff is a little bit higher quality than you would get from a cheaper printer. So I'm comparing to something like, a big common choice for a first printer is like an Ender 3. An Ender 3 is a printer that is like under $100. It's so cheap. And a lot of the things that I just talked about, doing that bed leveling automatically, all of the software stuff inside of here. So like the newer Prusas, if you run out of filament, the thing has a sensor and it knows that the filament ran out, and it'll stop and it'll beep at you. You put more filament in, and it just keeps going. Like stuff like that doesn't exist on a really cheap printer. That being said, ease of use. This was the third of 4 big things. If you are wanting to learn exactly how a 3D printer operates, take the ease of use and throw it the heck out of the window. Because the best way to learn something is to try to learn on something that doesn't do super well, where you're like constantly tinkering with it, maybe even modding it and stuff like that. So that's something you have to consider. But here, the Prusa does a lot of things for you. It figures things out, and it just works really well. The parts are quality. You know, I don't know exactly what factory, like if the motors come out of on an Ender 3 versus, I've got a pretty good idea where they come out of on a Prusa because they're the same factories that our trucks motors are. And I know that they are high quality. I know that they, you know, are a reputable source. The hot end on a Prusa is made by a company called E3D. E3D revolutionized hot ends. The hot ends prior to these had plastic tubes that went in, and the plastic tube actually dipped down into that hot zone. And if you printed something too hot, it would start melting that plastic tube. There is a little tiny tube inside of E3D's hot ends, but that's just to guide the filament down in between, you know, your heat sink and the actual melt. So the hot end on this is really nice. It's very consistent and creates a very nice consistent flow. The parts are readily available. Like if I need to swap out a part on my hot end, I can go to Amazon and either find, you know, a legit E3D part, or don't tell E3D I said this, but there's a lot of knockoff parts that you can find of the same exact thing that do just as well. The build quality of this is really nice. It doesn't move around a lot. Everything feels very tight. On a lower end printer, you may get some things where things are a little wiggly, and you have to consider that during your prints, if you have any portion of this machine that is a little out of tolerance and slightly wiggly, you're going to see that in your prints. You're going to see like little waves, and it's going to just not look nice and flat. So I'm dipping into number 4 here, and that's quality. A lot of the quality of a printer like this, like I said, comes from the development that Prusa has spent on. I like Prusa too because, like, this is a derivative of some of the original RepRap printer designs. So this company has been like iterating on this over time, and they're open source, and like just everything's awesome about them. So let's talk about like the lower end spectrum, right? So like an Ender 3. Ender 3s are really nice. Like if you are kind of questioning, do I get into 3D printing? How do I get into it in such a way that if I decide that I don't really like it, I'm not losing a ton of investment. So something like an Ender 3 or anything in that like $200 to $300 range is actually a really nice place to start. The things that you're going to have to deal with are some of the lower quality things on those machines. So you're going to end up like things like this, where it's like a really tightly built. You may have a little bit of wiggle. You may find yourself printing some sort of mod that stabilizes this palette. You may print pieces that ensure that the filament feeds into your process. One of the ways that something like an Ender or like a CR10 is cheaper is this on here. The extruder motor is right here. So the filament feeds in, the extruder motor pushes that directly into the hot end. Those printers have what's called a Bowden setup. So instead of this extruder motor being here, it actually sits off to the side, and there's a tube that feeds into here. The reason that is cheaper in general is that your hot end doesn't need to be heavy then. Like this has the weight of this motor that it's moving around, and like that's a lot to move around when you're constantly like going back and forth and doing all these things. So moving that weight off the side actually makes it so that these components up front here can be like of a little lower quality, because you don't have to make them so super structurally off. The problem with a Bowden tube is if you took, let's say you took, and this is a reference that I think you guys will understand, you took a 1/2-inch piece of PVC tube, and you took what would effectively be like a really long dart, right? That PVC tube is not the exact same diameter of that dart. So if you took one end of the dart and you put it into the tube and you went like this, the dart inside of there would actually bend a little. So you get a little bit of an inaccuracy every time this pushes in and pulls out and things like that. You get a little bit of an inaccuracy there. The advantage of having a direct drive extruder like this is that it doesn't exist. It's really accurate, really nice. So the fact that this printer comes with that is really nice. Like an Ender 3 or a CR10, you can work with the button system fine. You're going to spend a little bit of time tuning in your settings and things like retraction, speed, and length, and all of that. You can get them to print super nice. At no point in time am I going to tell anybody that like you can't print a nice print with $200. You absolutely can. It's the amount of effort that it's going to take you in order to get to those prints, especially if you pull the thing out of the box and it prints beautifully off the start. What's that print quality going to look like if you don't touch anything after the thing's been running constantly for years? You know, that it may degrade over time a little bit. It may not, right? So then you may want to start doing all these mods and stuff. So at that point, like I showed you the basic tools of the trade, the isotope alcohol, the thing to get off of it. On a cheaper printer, you may have to do additional things and additional mods in order to get that thing to consistently work properly all the time. I talked about the automatic bed level before. On lower end printers, that is not an automatic thing. The printer bot over here doesn't have automatic bed leveling. I actually found at the time that turning on like automatic bed leveling actually screwed the thing up. So what I did is I actually put small shims in that bed so that it was perfectly flat every time I went to print, and it stays like that pretty well because it's a solid ass machine. You know, you don't have this like flexible kind of PCB material. It's like an aluminum plate. On something, you know, on the lower end machines, you have these little knobs here with springs, and you have to turn that knob, and you do one on each corner. And if you get really good at this, it's not hard to do. It's really not hard to do at all. But you have to get it just right in order for your prints to come out nice. Sometimes those beds that you get are like a little warped, right? And then there's no amount of leveling that will fix that warp. You can get these corners perfectly level with each other, but what if there's a little bow in the middle? And then you're like, okay, well, I'm going to get a different piece of glass to put on here because I know that glass is nice and flat. All these things, not super expensive, but they are just like extra effort that you have to take. If you're, again, really interested in learning the ins and outs of all of these things and actually going through the trials and tribulations of all of it, yeah, get a cheap printer. Get something that is like within that budget range that if you decide that you don't like it or it doesn't work, cool, you're out, what, like $100, $200? I know that that's a lot for a lot of people, but it's much less than $800 to $1,000, right?
The pre-assembled is
Okay. So yeah, that was my list. It's material, and material I don't even really include in that. It is your budget, your ease of use, your quality. You decide that your ease of use or quality need to be much higher, then your price is going to raise up. We run Prusas because I don't like having to do all of those little. I like that this machine comes out of the box, and I can basically just put the thing together, and it's really easy to build as a kit. I feel like there's a ton of pieces, but as you're building it, you really start to see where all of the design effort and stuff has been put into this thing. And this is an older version. The newer versions are way easier too. But I really like that you can kind of pull a printer in this sort of range, and there are a lot of printers in this same price. This just happens to be the one that we like, but it's nice that you can kind of pull this out of the box, set it up, the thing kind of calibrates itself, will tell you if there are any issues in the build, if any of your parts are not working well. Kind of a plug and play type of thing. There, you know, it's not perfectly plug and play, and that's what you get into in much higher price machines. There is still a certain amount of like, I have to set exactly how high off the bed this thing is when it starts printing. You know, there's like a lot of little things that you have to get just right, but once you get them just right, it works really well, and they keep working over and over and over. Like when we're running these things in the farm, you basically can just start a print. When that one finishes, take it off, wipe down the bed, start the next print, rinse and repeat over and over and over. And yes, sometimes I have to replace parts. I keep replacement parts on hand. I keep fans, keep you know, nozzles in there. There are a number of things that you have to replace over time in order to keep the machine running really well. Bruce has really good support. So if there's something major on the machine that you got, they'll support you. And I've actually had them swap out a free power supply, totally free. And like, I don't know, that's cool. But once you get past this level, right? If you go into like a grade school or like a maker space that doesn't have like a 3D printing guru, you start getting into almost truly plug and play machines. So one in particular, like at my daughter's school, they have this Dremel machine.
That's proprietary.
Yeah. So like this has a lot of different replacement parts on it. You can put whatever type of filament roll you want. Like it's still a fairly DIY. When you get up into these higher end machines, this is going to sound bad, but if you don't really know what you're doing, but you want to get into a machine and show kids how to use it, you start getting into these high end machines that have a lot of proprietary things in them in order to make sure that that machine works perfectly the same thing every time. The biggest example of this is the MakerBot printer. MakerBot was a pioneer of 3D printing. They made a lot of really neat things, but at some point MakerBot went from open source and decided that they just wanted to sell the thing. Some of the things that MakerBot printers do is they take a proprietary roll of filament, and those filaments are their filaments, which that seems bad, but at the same time, when you have 8,000 different variables that can screw up the way that your printer prints, if you know that you are putting in something that is like a standard filament into that printer every time, you are essentially eliminating a variable from the situation. You know that that filament is going to go in there. And even though that filament is more expensive, you know that it's going to work. So they have stuff like that. The Dremel machine that I was talking about has a cloud system. So rather than on your laptop, you having a slicer and you take your model and you put it in the slicer and then you move that to an SD card and move it onto here, those machines will actually have internet connectivity on them. And what happens is you take your STL file and you move it up to a software in the cloud, and their machines magically slice it for you, and then through that network connection, dump that onto the machine. Again, something that seems, as a DIY person, to not be very nice, but you have to consider yourself in a school setting where you don't want to have a lot of hassle. So that Dremel machine is like $1,600 or something, right? That Dremel that they have.
Like 60 or something.
Yeah.
And it uses proprietary filament.
Yep.
And
So like it doesn't, like the quality of it and stuff isn't vastly different. If anything,
want to get some prints?
No.
Okay.
No. The quality is not vastly different, but what they are providing to you at cost is the ease of use. I would not say that anybody in the Nerf 3D printing world should ever buy a printer. There's no real reason for you to spend $2,000 on a printer. This I could see if you are like wanting to get into it really heavily and you wanting to print a ton all the time, and you want it to kind of work out of the box, but you also still want to kind of get your hands a little dirty. Like this level of printer is really nice, and you can get Delta printers in this level. If you again want to get into it at a very low level, you don't want to spend a ton of money, but you're okay with kind of tinkering with something, or you're okay with maybe swapping out a part with a higher quality part or something like that. Commander 3, really great. So, that makes that typical triangle of like you have 3 different things to choose from. Choose 2, and that's going to determine the printer that you buy. What did I started at 2, now 3:20?
You got 10 minutes.
Yeah, 10 minutes. That's my basic spiel, and I dragged that into about an hour and a half. I hope that helped you guys. I hope that was useful to some of you who already know 3D printing. If not, I'm sorry, but I'm sure it was helpful. It was good to talk to you guys, and thank you for tuning in. We do have 10 minutes. I have the YouTube feed going.
That's honestly all that people have been chatting on.
If anybody has questions, I can answer.
People were asking about supports at one point, as far as like.
Oh yeah, I never even mentioned. This is what happens when you wing a discussion. What were they asking about support?
When you were just talking about as far as print orientation and that kind of stuff, and like files, and like where do you choose to put supports, or do you just use a system?
Okay, so we talked about overhangs before. If you have a part that has like a really nasty steep overhang, you start using something that's called a support. Support is a very simple structure that sits underneath there, and as the print goes on top of it, it just gives something for it to kind of lay down on top. I try to design all of my stuff so that it doesn't take support. Supports are sort of like a last-ditch effort, where maybe you have something that's like, print the teddy bear. I don't know who made the teddy bear. Nature made the teddy bear, and teddy bear has crazy overhangs on it. Like, what do I do here? You put support on it. Support's really hard to use. I try to not use it, and it takes a lot of tweaking to get it working. I can't get on the internet.
Okay,
so
that's
I'm
fine.
relying on you to feed questions.
Okay. Any verdict on artillery printers? Do we know the Muffin Man?
I don't know.
Okay, well there we go. Have you tried toothpaste? No, we have not.
Toothpaste for
bed adhesion. Matt Becker asked that. I've never heard that before.
I could.
I've heard.
Yeah. So like PEI. Sometimes if you have an old PEI sheet, sometimes what you can do to kind of revive it is take a really fine grit sandpaper, and it'll create a porous surface again. I'm really pulling this out of my butt, but I could see using toothpaste as a way to create some pores on there. But no, I don't
see how that would work. Yeah. I don't know if it would work, but it would make your prints minty fresh. Matt. All right. I've just answered some of the questions. Multi-material color, like MMU. One of those.
Have we tried the MMU? No, we haven't. I'd really like to try an MMU. Really like to try a palette. Oh, dreamy.
Yeah, but we want printers. We need more printers first.
Not on budget.
Let's see. Oh, here, you know what? Show the coffee filament real quick for Havoc. Because we were talking about it in the chat.
Yeah, we didn't really get into a lot of filaments and why PLA is one of the reasons that we use PLA a lot is you can get it in a ton of different colors and stuff. And this is a really special thing. This brown rail on top of here actually has coffee infused in the filament. So when you print this, it smells like coffee in the room. Kind of neat.
It's super neat.
The same.
They have the tree one too, the Christmas tree.
Protopasta makes that. We really like Protopasta, and Protopasta actually has made a pine tree scented one in the past, where they actually take their Christmas trees from the year prior, grind them up, and then put that in filament. That's so cool. It's like not only does it smell like Christmas trees, but the Protopasta Christmas trees too.
Yeah. Yes, and whoever a destroyer, yes, that is my FDL. That's my FDL 2+. And it's missing some parts because our blasters are always in some kind of state of taking apart or putting back together.
Here, I'll put it like that, and then you can't see the missing part.
Inspiration was Twin Peaks. Those of you guys that actually know what Twin Peaks is, you would understand the coffee reference and why I had to use it on the rail.
damn fine.
Damn fine print blaster. All right, so you guys got 5 minutes. Oh, okay. Personal question as far as our favorite filament. I mean,
I don't really have a favorite. Okay, so
yes, you do. You have your colors.
Oh yeah. Okay. So I really like. It's right here.
Okay.
I'm a blue guy, right? Blue is one of my favorite colors. This blue on my blaster is high five blue that Protopasta makes. Protopasta makes a lot of really wicked, cool specialty filaments that has an ever so slight sparkle to it. And I really like that. Something you have to keep in mind, though, that like I don't really. This is just my personal opinion. I don't try to like any particular brand because every color within a brand is actually going to react differently when we go to print it.
Well, and also the colors that people have wanted their blasters and have chosen what filaments we end up using.
Yeah, like something like Hatchbox. Hatchbox is like our go-to common color filament. But like this blue is blue Hatchbox. This print's really nice. They're white and they're yellow for whatever reason. Whatever additives they add to that filament, the white and yellow are super brittle. This is awesome. If I did this with white or yellow, it would probably break. So even within different brands, filaments are yeah,
okay, so
Hatchbox orange is really good.
Mm-hmm. Except now that we have our safety orange, that's the only orange we like to use.
What's a good interface distance between the supports and the actual? I think when I've used supports before, it's been like 0.3. So it's just outside the scope of a single layer, a little bit more than a single layer. Apart from blasters, what do you folks print yourself? Everything.
But right now we're printing face shields.
Mostly blasters.
Like all we're printing.
Oh yeah, we're printing face shields right now. COVID stuff. But like I used to be a home brewer. I used to print my own or make my own beer, and I've actually printed parts to aid in the brewing process and stuff like that. And like lots of little things, little holders for stuff, or like little desk trinkets. I don't know. You've printed a bunch of stuff.
I print a lot of things.
Like little flowers. I printed a rose for her for Valentine's Day one year.
Yeah, it was the only one thing he's ever given me. But show that one.
Yeah, this is like a little flower.
But it's also
and the cool thing too is she one of our printer bots has this stuff called diffraction grating on its bed. I don't know if you can.
No, you can see it. Like here,
but the diffraction grating is.
You got to get closer.
No, you can see the rainbow a little bit. So it's sort of like when you made a kaleidoscope in school and you turned it and made all these colors. The diffraction grating on there creates that same thing on the surface of the print. Pretty cool. I'm just not going to answer this question.
Well, and it's 3:30.
Yep.
So I think that's it.
I think that's it. Hopefully Adrian's not still asleep. See you guys.